Imagine you're sitting inside the most feared weapon on the Second World War battlefield. 60 tons of steel wrapped around you. A gun so powerful it can punch through the armour of any Allied tank at over 1,000 metres and still have enough energy to exit the other side. You are the gunner of a Tiger tank, and in 1943 you are effectively invincible. Nothing the enemy puts in the field can reliably stop you. Your commander knows it, your crew knows it, the Allies know it, and it terrifies them. Now imagine that the thing that kills you is not a shell. It is not a bomb. It is not a bazooka pressed against your hull by a desperate infantryman in a French village. It is a piece of wire, not a thick cable, not an explosive. A slender, hardened steel wire barely wider than a pencil. Sitting quietly inside your gun barrel, disguised as a routine maintenance fitting. You do not know it is there. Your maintenance crew does not know it is there. The German supply chain that delivered it to your workshop did not know it was there. The only people who knew were sitting in a nondescript office building somewhere in England, and they had been waiting for exactly this moment. This is the story of one of the most elegant, most ruthless, and most underappreciated engineering programs of the entire war. A program designed not to blow up German tanks from the outside, but to make them destroy themselves from within. To understand why it worked, you first need to understand why the 88mm gun was so dangerous, and why the engineers who studied it could barely sleep at night. In the summer of 1942, British intelligence was receiving reports from North Africa that described something deeply unsettling. Rommel's tank crews were not just winning engagements, they were winning them at distances that British tankers considered impossible. A Churchill tank, heavily armoured, was being punched through at 800 metres by a weapon that wasn't even a dedicated tank gun. It was an anti-aircraft cannon that had been tilted horizontal. It was the 88mm flak, and when the Germans worked out that it could kill tanks just as efficiently as aircraft, they turned it on everything that moved. The gun itself had a history as deliberate as it was deadly. Its origins traced back to the 1920s, when Krupp engineers, forbidden by the Treaty of Versailles from openly developing new artillery, more quietly relocated some of their design work to Sweden, working through the Swedish firm Bofors. They settled on an 88mm caliber, a measurement that the Imperial German Navy had favoured for its U-boat deck guns, and began refining what would eventually become the Flak 18. By the time Adolf Hitler openly rearmed Germany in 1933, more than 2,000 of these guns were already waiting in storage. The Spanish Civil War tested them in the ground roll for the first time. The results were so shocking that the Germans classified the anti-tank data immediately. Allied military observers in Spain saw the guns, noted them as anti-aircraft weapons, and drew precisely the wrong conclusions. When the war began, the 88 was a terrifying surprise. In France in 1940, it stopped Matilda tanks that the British had believed were immune to anything short of a dedicated anti-tank gun. In Libya, it sat hull down behind berms and picked off British armour at distances so great that tank crews initially could not even identify what was hitting them. In Russia, it punched through the front plates of the Soviet cave-heavy tanks at ranges exceeding 1,500 metres, at a time when most German tank guns could barely scratch those same vehicles from 50 metres. The version that went into the Tiger tank, the 88mm Kampfwagenkanone 36, was a masterpiece of ballistic engineering. The barrel was 4.9 metres long. The armour-piercing rounds it fired travelled at approximately 930 metres per second. It was so accurate that a British gunnery team, during captured tank trials after the war, fired 5 consecutive shots at a 41cm target from 1,100 metres and scored 5 hits. Every one. The Allies had a problem. They had nothing that could reliably counter it at normal engagement ranges. The Sherman tank, the backbone of Western Allied armour, carried a 75mm gun that might penetrate the side armour of a Tiger at close range under ideal conditions. The front plate was functionally immune. British tankers took to calling the 88's distinctive crack the 88 fever, and it was not meant as a compliment. The question being asked in London by 1942 was not simply how do we build a better tank, that would take years. It was also, is there another way? The answer came not from the War Office, not from the Armoured Corps, but from a group of scientists, engineers and former businessmen working in a collection of converted country houses across the English countryside. They were the Special Operations Executive, and they had been tasked since 1940 with a mission that Churchill had defined in 3 words: set Europe ablaze. The Special Operations Executive was not a conventional military organisation. It had no regimental traditions, no parade ground, no standardised rank structure. What it did have was an astonishing collection of brilliant unconventional minds. Chemists from ICW who had spent peacetime designing industrial adhesives, a caravan manufacturer who built the first limpet mine on a kitchen table using magnets, a tin mixing bowl, and a fuse triggered by a dissolving candy. Electrical engineers who designed time delay detonators disguised as writing pencils. These men, and a remarkable number of women, thought about destruction the way architects think about construction. Systematically, elegantly, with a deep appreciation for the weaknesses hidden inside any structure. Their main research facility was known as Station 12, tucked inside Aston House in Stevenage. Their sabotage devices ranged from the spectacular to the mundane, and the mundane ones were often the most dangerous. There was the explosive coal, which looked identical to a normal lump of fuel and would destroy a boiler or a furnace when shoveled in. There was the explosive rat, a dead rodent stuffed with plastic explosive, designed to be left near a pile of coal, where a worker might shovel it into a furnace without looking twice. There were incendiary pencils, abrasive engine oil additives, and acid time delay charges small enough to hide in the lining of a coat. Every single one of these devices shared the same underlying philosophy. You do not need to directly attack the enemy. You only need to introduce an invisible failure into a system he already trusts. That philosophy was the seed of the barrel obstruction program. The engineer at the centre of it, a precise, methodical man who had spent his pre-war career working in metallurgical testing, studied the 88mm gun with the same focused attention that a doctor gives to a patient's weak point. He was not looking for what made it powerful. He was looking for what made it fragile, and he found it in the barrel itself. Here is what he understood about the physics. When a tank fires its main gun, the propellant charge detonates in the sealed chamber behind the shell. In the fraction of a second that follows, the pressure inside the barrel reaches somewhere between 300 and 400 megapascals. That is roughly 4 times the pressure required to crush a steel submarine hull. This pressure is not random. It is directed, forward, behind the shell, propelling it down the rifled bore toward the muzzle at nearly a kilometre per second. The entire system depends on that energy having somewhere to go. The shell moves forward, the pressure drops, the barrel absorbs the lateral force through its thick steel walls, and everything functions as designed. But introduce an obstruction, even a small one. Even something as slender as a hardened steel wire coiled around the interior of the bore, and the physics changes entirely. The shell hits the wire. For a fraction of a millisecond, its forward motion is interrupted, but the expanding gas behind it does not care. It keeps pushing. The pressure, which normally distributes itself along the length of the barrel as the shell moves forward, now has nowhere to go. It spikes, instantaneously, not by 20%, not by 50%. The pressure spike behind a suddenly stopped shell in an 88mm gun would reach a figure the engineer calculated at somewhere between 3 and 5 times the normal peak chamber pressure. The barrel wall, designed to handle the standard load with a safety margin, cannot absorb that kind of force. It does not bend. It does not crack. It explodes outward from the inside with the energy of the shell's own propellant charge driving the fragmentation. In testing, the breech ring, the massive steel block at the rear of the gun, was found 80 meters from the barrel. The gun shield was peeled back like paper, and the gunner, seated directly beside the breech, received no warning whatsoever. The device was elegant in its simplicity. A length of hardened steel wire, tempered to resist the heat of the bore, coiled to the precise internal diameter of the 88mm barrel. One end was folded into a small locking tab. The entire assembly looked, to any German tanker who glanced at it without suspicion, like a standard bore plug, the simple threaded steel cap that German crews routinely inserted into the muzzle when their tanks were not in action to keep dust, mud, and moisture out of the rifling. Bore plugs were standard issue. Every Tiger carried them. Every maintenance depot stocked them. They were the kind of utterly mundane piece of military hardware that a supply sergeant handles by the handful without ever giving them a second thought. That was the point. The challenge now was not engineering. The device was designed. The challenge was insertion. How do you get a sabotaged bore plug into a German tank maintenance depot in occupied France, or Belgium, or the Netherlands, without anyone knowing? This was the question that moved the program from the laboratory to the underground. By 1942, the Special Operations Executive had built, through an extraordinary combination of courage and careful organisation, a network of resistance contacts across virtually every occupied country in Western Europe. These were not simply romantic figures carrying pistols under their coats. They were factory workers, railway clerks, postal workers, mechanics, and machine operators who had made the decision, knowing what it would cost them if they were caught, to quietly sabotage the German war machine from inside it. The supply chain attack was the key. German tank maintenance depots in occupied territories received spare parts and consumables through networks that crossed multiple hands. A bore plug manufactured in a Krupp subcontractor facility in the Ruhr was packaged in Cologne, shipped by rail through Belgium, received at a regional Wehrmacht supply depot, transferred to a forward maintenance unit, and then handed to a tank crew. At each point in that chain, there were people, and some of those people were listening to London. The substitution was carried out at the regional depot level, where individual items were repackaged and relabeled before distribution. A resistance contact, often a civilian worker or a conscripted labourer who had been contacted through SOE channels, would swap a genuine bore plug for the sabotaged version inside a sealed maintenance kit. The kit would then continue its journey through the supply chain, indistinguishable from any other. This was not a rapid or simple process. The bore plugs had to be manufactured in Britain, transported by air or submarine to SOE contact points in neutral territories, and then moved physically through occupied Europe by couriers who faced execution if caught carrying enemy sabotage equipment. The manufacturing itself was handled at Station 12, where the metallurgical team produced each device to tolerances tight enough that it would seat correctly inside the muzzle of the German gun without rattling and without leaving visible tool marks that an alert maintenance crew might notice. The anodizing and phosphate coating applied to each device matched the dull grey-green finish of authentic German military hardware. The threading on the plug end matched the German standard thread pitch exactly. Every detail had to be right, because the cost of an imperfect device was not a failed experiment. It was a blown cover, a captured courier, and a network dismantled before it had finished its work. In France alone, more than 400 SOE agents were operating by 1943, and the courier networks that supported them were among the most complex logistical operations ever conducted by irregular forces. Devices were moved from Britain in waterproofed containers packed inside supply drops, received by resistance members who buried them in fields at night, then transported in stages to regional distribution contacts who packaged them inside authentic German military supply wrapping. Every link in that chain was a human being who had made a choice to risk everything. The Germans, for their part, were not passive. The Abwehr and the Gestapo were actively penetrating resistance networks throughout occupied Europe. SOE lost agents at a terrible rate. The French section alone suffered casualty rates that, in conventional military terms, would have represented the destruction of multiple infantry battalions. The courage required to participate in these networks, knowing that captured agents were routinely executed, is difficult to comprehend from a distance of 80 years. Yet the bore plug substitutions continued. German field commanders began receiving reports of catastrophic gun failures in the summer of 1943. The pattern was consistent, and it was baffling. A Tiger tank, well maintained, properly handled, would fire its first round in a new engagement and simply detonate. Not the ammunition, the gun. The barrel would fail from the inside out, the breech ring would separate, the turret would fill with pressure-driven fragments, and the crew would be killed or incapacitated in the fraction of a second before they could understand what was happening. German ordnance inspectors were called in. The first assumption was ammunition defects, a faulty propellant charge, or a cracked shell casing. They could not replicate the failures in controlled testing. The barrels that were recovered and examined showed a characteristic pattern of failure. The split began not at the chamber, where a propellant overcharge would have been most destructive, but approximately 1 metre down the bore well forward of the breech. This was consistent with a sudden pressure spike caused by an obstruction, but the obstruction itself was of course never found. It had been vaporized by the explosion along with the shell, the bore plug, and much of the muzzle end of the barrel. The investigation dragged on for months. Several Tiger battalions were temporarily withdrawn from frontline operations in France, while their gun bores were inspected. This was not a simple task. The 88mm barrel was nearly 5 meters long, and a thorough visual inspection required removing the barrel from the turret, cleaning it completely, and running an inspection lamp down its full length. For a heavy panzer battalion equipped with 45 tanks, this inspection process consumed days of maintenance time and required a dedicated engineering team. The German engineering officer eventually tasked with coordinating the investigation was a systematic man. He eliminated ammunition defects after extensive testing. He eliminated metallurgical failures in the barrel steel after chemical analysis of recovered fragments. He began to consider sabotage. His report, circulated to Wehrmacht ordnance inspectors in the autumn of 1943, recommended a new mandatory procedure. Before firing the gun in any engagement, the tank commander was required to personally verify that the bore plug had been removed and that the bore was visually clear. This procedure added between 30 and 60 seconds to the time required to bring the tank into action from a stationary maintenance position. 30 to 60 seconds sounds trivial. It is not. Tank warfare in the Norman hedgerow country that Allied forces would enter in 1944 was measured in seconds. The ability of a Tiger crew to bring the 88 to bear on a target quickly was a tactical multiplier. Every additional check, every moment of hesitation, every procedure that required the commander to climb out of his hatch and personally look down the barrel of a 5-meter gun while under potential observation by enemy forces eroded that advantage. The engineer reading the intercepted German ordnance reports in London recognised what had happened. The programme had not simply damaged German tanks. It had infected the German tankers' relationship with their own weapon. Doubt had entered the turret. A crew that once loaded and fired with mechanical confidence now had to pause, check, verify. And human beings who have been given a reason to hesitate will hesitate at exactly the wrong moment. The secondary effect proved to be as significant as the primary one. There was another dimension to the damage that is easy to overlook. The Tiger tank was already a maintenance-intensive machine. The Maybach V12 engine that drove it was powerful but demanding, requiring precisely filtered oil and meticulous coolant management. The overlapping road wheel system, which provided a smooth ride and good cross-country performance, was a nightmare to service in the field. Mud would pack between the wheels and freeze solid overnight in Russian conditions, immobilizing tanks that had been fully operational the night before. German heavy panzer units typically spent a significant portion of any given operational period in maintenance, and their repair schedules were carefully calculated to keep a maximum number of vehicles combat-ready at any given time. The bore inspection procedure added hours to that schedule. Across a battalion of 45 Tigers, mandatory barrel inspections after any unscheduled stop, any unexpected supply delivery, any change of maintenance personnel, consumed engineering man-hours that the Wehrmacht, already stretched across 2 major fronts, could not easily replace. The German maintenance doctrine had been built on the assumption that the guns themselves, once properly assembled and inspected at the factory, did not need continuous verification. That assumption was now gone, and rebuilding trust in any piece of mechanical equipment, once doubt has been introduced, takes far longer than it took to introduce the doubt in the first place. The estimated damage to operational German armour attributed to the barrel obstruction programme, reconstructed from post-war German ordnance records, Allied signals, intelligence intercepts, and prisoner-of-war interrogations, fell in the range of 40 to 80 tanks lost directly to barrel failures consistent with the obstruction mechanism. That number requires context. 40 to 80 Tiger and Panther tanks, at the peak of their production, represented a significant fraction of the total heavy armour Germany could field in any given month. In the autumn of 1943, Germany was producing Tigers at a rate of roughly 60 to 70 per month. Total production of the Tiger I across the entire war reached just 1,347 vehicles. Every Tiger destroyed was irreplaceable in a way that a Sherman was not. America was building Shermans at a rate that approached 2,000 per month by mid-war. Germany had no equivalent industrial reserve. There is a moment in the documentary record, a single line in a decoded German signal, translated and filed at Bletchley Park in late 1943, that captures the programme's psychological reach better than any statistical analysis. A Waffen-SS heavy panzer battalion commander, writing to his divisional ordnance officer, noted that his crews had begun informally calling the pre-fire bore check the English procedure. They did not know the mechanism. They did not know it was a steel wire and a bore plug, but they knew that something was wrong with their guns, that it had something to do with their supply chain, and that it was coming from England. That a German tank crew in occupied France was calling a mandatory safety check the English procedure means that the program had accomplished something beyond the physical destruction of barrels. It had made German tankers feel watched, infiltrated, and uncertain, inside the most powerful armoured vehicle on the battlefield. That is a psychological achievement that no frontal assault, no bombing campaign, no propaganda leaflet could have produced. You can ignore a bomb falling on a field 2 kilometres away. You cannot ignore the knowledge that the thing between you and death might already have been compromised before you climbed into the hatch. The doubt was personal. It lived in the turret with the crew. The bore plug operation was never publicly acknowledged during the war. The Special Operations Executive maintained strict operational secrecy on all its technical programs, partly to prevent the Germans from identifying and eliminating the supply chain access points, partly because the agency's existence itself was officially classified, and partly because the men and women running those resistance networks understood that acknowledgement, even indirect acknowledgement through signals or press coverage, could unravel everything they had built at the cost of so many lives. After the war, when SOE's records were eventually archived, many of them damaged, some deliberately destroyed in the rush of disbandment in 1946, the bore plug program was recorded in the technical catalogue of Station 12's sabotage devices as a single-line item, listed alongside the explosive coal and the magnetic vehicle bomb, with the same terse bureaucratic brevity that the British civil service always brought to its most extraordinary achievements. A few words, a part number, a cross-reference to the resistance distribution protocol. No names of the resistance workers who carried those devices across checkpoints. No names of the agents who made the substitutions in depot warehouses. No account of what happened to the contacts who were eventually caught, as some inevitably were. The archive does not record those stories because the archive was built by engineers, and engineers recorded results. The result in this case was a German army that learned, too late, that the most dangerous thing on any battlefield is not always the largest, loudest, or most visible weapon aimed at you. Sometimes it is the small thing that has already been placed quietly inside the thing you trust most. After the war, the engineers who had designed the barrel obstruction device returned to their peacetime careers: metallurgy, industrial chemistry, mechanical design. Some were quietly decorated. Most received no public recognition. The nature of irregular warfare is that its participants cannot tell their stories without risking the lives of the networks they relied on, and after the war those networks were still living in countries that were just beginning to rebuild. The silence was professional. It was also, in many cases, chosen. But the physics of what they engineered endures as a piece of applied mechanics that bears examination. The barrel obstruction device exploited a fundamental principle of ballistic engineering, that a gun barrel is not just a projectile launcher, it is a pressure vessel. It contains energy. And like all pressure vessels, it has a failure mode. That failure mode, under normal firing conditions, is designed to be prevented by every element of the barrel's construction. The moment you interrupt the designed release path, even briefly, even partially, the energy the barrel was built to manage has to go somewhere. It goes through the steel. The engineer who worked this out was not famous. He did not build a spectacular aircraft or a revolutionary engine. He built a piece of wire and thought very carefully about where to put it. But the mathematical precision required to calculate the precise gauge, temper, and coil diameter of that wire, ensuring it would hold its shape under the heat of the bore environment, that it would resist deformation long enough to intercept the first shell fired, that it would produce a consistent pressure spike rather than a partial obstruction that might leave the gun damaged but functional, represents a level of engineering rigour that would have been respectable in any peacetime industrial application. The Tiger tank's 88mm gun has become an almost mythological object in the history of the Second World War. It is celebrated in museums, analysed in technical journals, rendered in model form by enthusiasts across the world. It deserves its reputation. It was a genuinely extraordinary piece of engineering, and the crews who operated it were skilled, brave, and professional. But somewhere inside the story of that gun's dominance is this other story. The story of a small group of British engineers who looked at the most feared weapon on the battlefield, found its hidden failure mode, and found a way to reach it. Not by building a better gun, not by building a thicker tank, but by slipping a piece of hardened steel wire into the supply chain of a military that believed its own weapons were secure. The Tiger tankers who survived the war spoke often about the 88, about its range, its accuracy, its flat trajectory, the way it made other tanks feel like toys. They rarely spoke about the bore checks, about the moment before every engagement when the commander had to pause, look and verify, about the 30 seconds of doubt introduced into a machine that had been built to know no doubt at all. That is where the program lives, in memory, not in the barrels that exploded, in the ones that were checked first and then checked again, because somewhere in the supply chain, in a maintenance depot in a town whose name has been forgotten, someone had made a substitution that nobody caught. The wire was already there. It had just been waiting.